Okay, very good afternoon to all the student participants who have assembled here to learn about the electronic simplified and industry oriented course, a practical approach. So, only 5 students are there here. One student got OD, event called. So, still 10 students has to join, but we are unable to wait further. We will enter into the session. So where we are now traveling in is we have completed our first module last week. First module, what we have seen is the basics of circuit components. We have discussed basics of circuit components like resistor, capacitor, then sensors, switches, relays, multimeter, and basics of soldering practices also we have done it. I asked you to go through some YouTube videos also if you want more details about these basics. I also shared some links and I asked you to go through some other links also so that you can get familiarized, you can get more idea, more basics about the circuit components that is what I told in the last class. Good. Now we will be moving to module 2. So as a whole, I want to tell you this industry-oriented course is a tool from which you can understand basics about the core papers. Okay. So we are having totally only 3 modules, out of which we have completed first module, and we will be switching now to the second module, wherein we are going to see again the basics, but of various devices we will see. So first module, we have seen the basics of circuit components. And now in the second module, we will be seeing the basics of devices, electronic devices. So very simple module, like the first module. This module also is a very simple module. We are going to cover just 4 basic electronic devices. Number 1, we are going to see PN junction diodes, number 1. Number 2, Zener diode. We will be going into either Zener or Zener. How will you pronounce? You can do it in on your own way. Zener diode is the second topic. Third device, what we are going to cover is a very important device. We call it transistors. And finally, digital ICs is the fourth. For all these sorts of electronic devices, we are supposed to see their specifications, how they will be specified. For example, if I want to go and purchase a diode in an electronic shop, how we have to go and ask? Okay, there comes the importance of specifications. For example, if not only diode, whatever may be the device we want to purchase. For example, if you want to purchase a bulb, a 0-watt bulb, you have to mention there the wattage, 0 watt. So it will not consume any power. Okay, like that. 40-watt bulb, in the sense, if we have to mention whether it is a fluorescent lamp or it is an incandescent lamp or a CFL bulb or a LED bulb, we have to mention. There comes the importance of the term specifications. Along with that, their properties and some of their applications. These also plays a very important role in our circuit components and devices, right? So my plan is to go for first 2 devices today and next 2 devices in the next class. So fortunately, by next Wednesday, we can complete second module. Very simple module. but its duration in the syllabus will be 5 hours, but 5 hours is not required. Okay. So this is the plan for the second module of IOC. If there is some disturbance like CAA2 or like your placement, technical training, if something is happening, then obviously we may not find time to complete it. But this class, we got one particular class, so we can complete half of the unit. First 2 devices we will complete. Then in the next Wednesday, we will be completing the next 2. Very simple, diodes. So in diodes, we are going to cover PN junction diode and Zener diode, or I can say Zener diode, whatever it is, right? So we will go to the PPT now. And after the class, please students, don't leave the session immediately if I said thank you. We remain in the class till the attendance has been taken, because it is a Google Meet, not like morning class. Morning it was go to meeting, so attendance will be monitored by the tool itself. Okay, this is Google Meet. There may be some errors in the Google Meet attendance. That is why, along with that particular attendance, I am taking oral attendance also. Okay, so before taking the attendance, you are requested to remain in the classroom. Don't leave the classroom. Okay, this is a small request I want to give it to you. Fine. With this particular brief of our course, let me share the PPT for today. 1 minute. Yeah, is my screen visible? Is the PPT visible to you? Yes, guys, are you there? Whether the PPT is visible to you? Yes. Thank you. Thank you, Sri Vishnu, for your response. I'll make it full screen. So module 2, module title is electronic devices. We are going to cover PN junction and Zener diodes in this particular module. Okay. Coming to the agenda of this particular unit or this particular class. It goes like this. We will be revising what we have seen in the last class. So last class we have covered the last topic of the first module, that is relays, multimeter, and basics of soldering. Relays, multimeters, and basics of soldering. That is what the topic we have covered in the last class. I have shared some videos also, some YouTube links also. I hope you might have seen some of the videos related to relays, multimeters, and soldering, their applications, properties, specifications, data sheet parts, and types also, right? Today, we will be entering into electronic devices, which is our second module, start. So 2 devices, we are going to cover it today, along with their specifications, their applications, and their properties. The devices are PN junction diode and Zener diode. We will summarize and we will go finally for oral attendance. Coming to the course outcome, as I said, we are in second module. So CO1 is going to be a common CO for 2 modules, module 1 and module 2. Right? So module 1 we have completed, module 2 now. So the CO course outcome is summarize different types of circuit components. Circuit components means it goes to module 1. Devices, if I tell, it comes to module 2. Summarize different types of devices with specifications, properties, and applications. Summarization in this sense, it is actually apply level, K3 level of Bloom's taxonomy. That is what. So CO1 is summarize different types of circuit components and devices with specifications, properties, and applications. That is what is the actual course outcome. About the course, module 2 is very simple, as I said. Basic electronic devices, which will be allocated 5 hours, but 5 hours is not required. We are actually now sitting in the 6th hour of the class. First hour we had introduction of the course. Second hour we completed resistor. Third hour we have completed capacitor. Fourth hour we have seen two devices, sensors and switches. And fifth hour, last week we had relays, multimeters, and soldering. So today is the 6th hour, and we will be completing PN junction and Zener diodes, their properties, data sheet, or I can say specifications and applications we will go into. Okay. So this particular points you might have done it already in your second sem in a paper named semiconductor physics. Okay, and this diode is actually a very basic thing. Okay, which you might be doing it or learning it from your 12th standard physics paper. Okay, so first of all, what is a junction? How a junction is getting formed? That is the primary thing which is required. So here, by joining a piece of p-type material to a piece of n-type material in such a way that their crystal structure remains constant, remains unchanged, or I can say remains continuous. If I join these two, then I'll get a junction. PN junction is thus formed. Simply speaking, how a junction is formed is in this way. Can anyone answer or give some examples of p-type material and n-type material? Can anyone volunteer yourself? P-type material example, at least one or two examples, and in the same way, N-type material, one or two examples. Can anyone tell the answer for this? Okay, otherwise I'll pinpoint. Mitul of Easy B. Are you there? Mitul? Can you unmute yourself?
Yes, sir.
Yeah, good afternoon, Mitul.
Yes, sir.
Okay, you got my question, what I asked?
Sir, can you repeat once more, sir?
Can you tell some examples of a p-type material? You might have studied in your chemistry, right? I think you're searching in your Google. Okay, do it at least. No issues. Examples of p-type material. Yeah, what happened, Mithul?
Sir, don't know, sir.
In Google also it is not coming.
I didn't Google, sir. Once.
Hmm.
Boron, indium, or gallium.
Okay, good. Thank you, Mithul. Thank you. So, boron is the basic material. For example, I can say, right, boron, indium, these things will form the basic material for a p-type material. We can say that there must be p-type. Anybody from C section, can you answer? Give some examples of n-type material. Maybe Ranjit. I think Ranjit also belonged to B section. Okay. Uh, who else is available from C section? Prabhu. Prabhu K, are you there?
Yes, sir.
Yeah, Prabhu, good afternoon.
Good afternoon, sir.
You got the answer for N-type material examples?
Sir, actually, I don't know, sir, but it is made up of group 5 elements, I think.
Pardon?
Uh, I don't know, sir, but it is made up of group 5 elements.
Group 5 elements.
Yes,
Okay.
sir.
Okay, fine. Okay, thank you, Prabhu. Thank you.
Thank you.
Anybody knows the answer? Um Maybe Sri Vishnu, I'll go for. A lateral entry student. Let us try with Sri Vishnu. Sri Vishnu,
Yes, sir.
can you give the example for N-type material, Sri Vishnu? Very basic material I want.
I don't know, sir.
Yeah. Okay. Okay, Vishnu. Thank you. Raylan has given the answer in the chat box. Phosphorus. Phosphorus is a material which I can call it as an N-type material, right? Okay, good. So, as I said, without disturbing their crystal structure, if I join boron and phosphorus, right, what will happen is junction gets formed. We call that as PN junction because P-type material, N-type material, they are joined together to form a junction. So where it finds its application, that matters a lot. It can be used as a rectifier, amplifier, switch, and other operations in electronic circuits. So this thing can find its application in these areas. Right. A PN junction cannot be produced by simply pushing two pieces together or by welding, etc. See, if I want to join two iron pieces, as I said in the last class, right, I cannot go for some sort of pasting or some sort of bonding like that. Okay, what I have to do, I have to go for welding because two big iron rods cannot be pasted with a simple 5 rupee pevy stick. Do you agree? So we have to go for some sort of welding, right? But it is not, or this junction cannot be produced by means of welding because these are small electronic devices. Okay, so because it gives rise to discontinuities. If I go for welding, right, what will happen? The crystal structure will definitely get damaged. But our main criteria here is crystal structure should not be damaged in such a way that we have to join the pieces. Okay, for that, what I am going to do is I am going to use some special fabrication techniques to create that particular PN junction. Okay, a PN junction is a device formed by joining p-type. P-type means doped with boron, aluminium, indium, and n-type. N-type means doped with phosphorus, arsenic. Semiconductors are separated and separated by a thin junction is called a PN junction or junction diode. Simply, we call it as a PN junction diode or as a junction diode. That's all. Right? That is what is the point. Now comes a question. This question is to maybe Kritika. Kritika, are you there? Kritika, please unmute yourself. Don't come to the chat box. Please unmute yourself. Yeah, Kritika. Good afternoon. Good afternoon, Kritika. Yeah, Kritika, you are audible, but your sound is very less.
Sir, good afternoon, sir.
Yeah, good afternoon. Now you are audible. Good.
Yes, sir.
Can you tell me, Kritika, what is meant by doping?
Doping, yes, sir.
Yeah. Yeah, what happened? You are still searching? The answer is not coming, yeah? What is meant by doping? Mic not working. Okay, very good. Kritika, you can put it in the chat box. It's okay. Can you answer me in your chat box? Okay. Modulating its electrical properties. Okay, I think that is the answer. You're getting it from Google. It's okay. I'll tell the answer. Raylin, you know? Anybody knows what is meant by doping?
So I think it's addition of impurities.
Yeah, very good. Very good, Raylin Celicia. Thank you so much. So the answer, what Raylin has given is the exact answer. Adding impurities to a pure semiconductor. Adding impurities to a pure semiconductor is we call it as doping. Is the process we call it as doping. Adding impurities to a pure semiconductor is the actual answer. Okay. In that way only we can form a PN junction. Right? So that is what is the answer I actually anticipated. Good. So electronic symbol for a PN junction diode is shown at the bottom. You can see. So as far as the size of p-type is concerned, it is in between, moderate. N-type, its width is large, and junction or the depletion layer is shown in between N-type and p-type. It will act as the insulator between p-type and N-type material. So in PN junction diode, N is at right and P is at left. Majority carriers of N region will be electrons, and for P region it will be holes. How a depletion layer is getting formed? The excess electrons in the valence band in the N region cross the junction and combine with the excess holes that are present in the P region. Holes are positively charged, electrons are negatively charged. We know that already, right? At one point, the migratory action is stopped, and additional electrons from the N region are repelled back by the net negative charge of the P region. Similarly, an additional hole from the P region are repelled by the net positive charge of the N region. Net result is a creation of a small layer of each side of the junction will be formed, which is depleted, or I can say emptied of mobile charge carriers. There will be no charge in the depletion layer. Just that particular layer which is present in between p-type and n-type material, that I am going to call it as a depletion region or depletion layer, whose thickness will be in the order of micrometer. In this way only depletion layer is getting formed. The depletion layer contains no free and mobile charge carriers, but only fixed and immobile ions will be there. And the width of the depletion layer purely depends upon how far the doping is done, or doping level is according to the doping level. Okay, here this thing, width of the depletion layer will be decided. If it is heavily doped, then I will have thin depletion layer. For lightly doped, I will have very thick depletion layer. Next comes something called potential barrier. So the electrons in the N region have to climb the potential hill in order to reach the P region. So electrons trying to cross from the N region to reach P region experience a retarding field, that is negative acceleration of the battery, and therefore repelled back. Similarly, for holes from P region will also take place. Potential thus produced is, I am going to call it as a potential barrier. For silicon make diode, okay, its value is 0.7 volt, and for germanium make it is of 0.3 volt. Very popular things. PN diode. PN junction can basically work in two modes. One is we call it as forward biased, another one we are going to call it as a negative bias. When I can say the diode is forward biased, so a positive terminal of the battery, if it is connected to the P region of the P-type of the material, and the negative terminal of the battery, if it is connected to the N-type material, then I can call that particular mode of operation as a forward biased mode. Reverse biasing means opposite one. That is, the positive terminal of the battery is connected to the N-type material. Negative terminal of the battery will be connected to the P-type region. If that is the case, it becomes a reverse biasing. Forward biased condition, what happens? It forces the majority charge carriers to move across the junction. Therefore, what happens is width of the depletion layer gets decreased. Once the width of the depletion layer is getting decreased, means what will happen is it allows the current to flow from one region to another region. Or I can say flow of charge carriers will be taking place as the width of the depletion layer is minimized. So what happens? Current is allowed means it will act as a switch. Okay, so what happens is once the junction is crossed, a number of electrons and the holes will start their recombination. For each hole in the P section, P region, that combines with an electron from the N section, a covalent bond breaks and an electron is liberated, which enters the positive terminal, thus creating a pair called electron-hole pair. These basics you know already, right? So current in the N region is carried by electrons, and in the P region it will be carried by holes. These things we know. Reverse biasing, what happens is depletion layer gets widened. Why? Because negatively charged polarity, negative terminal of the battery will be connected to the P type. So P type, we have got hole material, it is a negative one. So what happens? Opposite poles attract each other. That means towards the battery, holes are attracted. In the same way, towards the battery positive, electrons are attracted. That means what will happen, that particular pulling action will take place. So my depletion layer gets widened. Okay, gets widened in the sense that is a heavy resistance. If it is heavy means automatically my current will get reduced. So current will be in the order of microamps as far as the reverse biasing is concerned, and forward biasing, the current will be in the order of milliamps. Okay, so that is the point I want to tell over here. As if I come to VI characteristics, the curve drawn between voltage across the junction along x-axis and current through the circuit along the y-axis, they describe the DC behavior of the circuit. When it is in forward biased condition, no current flows until the barrier voltage, or I can say potential barrier, 0.3 for germanium and 0.74 volt for silicon is overcome. Then the curve has a linear rise and the current increases. Okay, therefore the forward current, what will happen, it will increase very sharply. So there is a curve also I have drawn it, you can see to it. VI characteristics with the reverse biasing. In reverse biasing, what will happen, potential barrier at the junction increased. Junction resistance also increases and prevents the current to flow. Maybe current, if it is flowing, it will be in the order of microamps only. However, the minority carriers are accelerated back by the reverse voltage, resulting in a very small current. We call it as reverse current, which is in the order of microamps. When reverse voltage is increased beyond a value called breakdown voltage, the reverse current increases sharply and the diode shows almost zero resistance. Zero resistance means current will be very, very high. It is known as, we call it as avalanche breakdown. So reverse voltage, if I apply it above 25 volt, definitely it will damage the junction. So beyond 25 volt, we cannot, or we should not increase the reverse voltage. Yeah, this is the graph I want to show you. So forward biasing, 4 quadrants are there. Forward biasing, this is reverse biasing. So in reverse biasing, we have got avalanche breakdown. In Zener diodes, we'll be having the Zener breakdown, but in ordinary diode, we are going to have avalanche breakdown. So current, how it rises during forward biased condition and reverse biased condition is clearly shown here. So this particular PN junction is going to act as a switch. That's all. It's a very simple thing. It's going to act as a switch. Whenever it is forward biased, switch will be closed. Otherwise, switch will be opened. Okay, and this particular diode will be helpful to design a rectifier. Rectifier and all, we will see it in the third module. Okay, so PN junction diode acts as a rectifier as seen in the VI characteristics, which is shown above. Certain current flows in forward biased mode, and negligible amount of current only flows in reverse bias mode until Zener or avalanche breakdown happens. So until that particular breakdown occurs, no current flows, I can say, or very minimal current in the order of microamps only flow. Beyond that, the current value increases actually. Once that breakdown occurs, then automatically my reverse current increases sharply. Okay, that is what is the point I want to convey. All right. Thus, the PN junction diode allows the electrons flow only when P is positive. This property is used for the conversion of AC into DC, which is called rectification. That's what I said, rectifier. Automatic switch is, as I said already, when the diode is in forward biased mode, the switch is said to be closed, and when it is in reverse biased mode, switch is said to be open. Coming to advantages, no filament is required here for its operation. It occupies very less space only, less floor area, and long life it will give. Right? As far as the applications are concerned, as I said, the switches, rectifiers, all these things. It is used as rectifiers to convert AC into DC, number one. It is going to be used as a switch in computer circuits, number two. It is used as detectors in radios to detect audio signals, in radio detections, or in radars. These points are very big applications. And it is used as a LED to emit different colors. What is LED actually? Anybody knows? What is the full form of the word LED?
Light emitting diode.
Yeah, light emitting diode.
diodes.
Yeah, very good, very good. Light emitting diode means, can anyone guess what is the basic difference between ordinary diode and LED? What is the basic difference? How it shows the output, that makes the difference, okay? Can anyone guess what may be the output or difference between LED and diode output? Okay, as its name tells, LED is a light emitting diode. So whenever diode is forward biased, or whenever the switch is closed, or whenever it is operating, okay, what will happen is a light will be emitted. That is the difference. If light is glowing, that means that it is forward biased. Diode is forward biased. If light is in turn off position, it is a reverse biased condition. That is a well-known fact. Okay, this is regarding PN junction diode. Next, we will enter into Zener diode. Okay, its introduction. A Zener diode is a particular type of diode that allows current to flow not only from its anode to cathode, but also in the reverse direction when the so-called Zener voltage is reached. So, along with reverse breakdown voltage or potential barrier, as we discussed, here there is some voltage called Zener voltage. Once that, Zener voltage is reached, we will be having here a reverse operation also. In the reverse bias also, it finds its operation. That is what is the speciality of a Zener diode. So Clarence Melvin Zener, the American physicist, he is the person who invented Zener diode. Zener diode introduction. The Zener diode is a silicon PN junction devices that differs from rectifier diodes, that is ordinary PN junction diodes, because it is designed for operation in the reverse breakdown region. That's what I said. In reverse breakdown, ordinary junction, what happens is in the order of microamps only, it will be going to give the current depletion layer, or width of the depletion layer gets widened. So what happens is current gets reduced. Okay, but if I use a Zener diode, that particular thing can be rectified. The basic function of Zener diode is to maintain a specific voltage across its terminals within the given limits of line or load changes. Look at the diagrams here. Depletion layer, P layer, N region is there. Depletion layer is there in between P and N. So anode and cathode are available. Its symbol looks like this. Anode will be taken as plus and cathode will be taken as negative. Ordinary diode will have a straight line at the cathode, but here at the end there are some tilt. Okay, that is the actual difference between or difference in the symbol of diodes are concerned. Then if I give a diode which is like the third picture from left to right, okay, you can see it is a Zener diode. And can anyone guess which terminal is anode, which one is cathode? Can anyone guess from the third picture? Yeah, can anyone guess which terminal is anode, which terminal is going to be the cathode? Okay, I think you cannot guess that. See the black band, you can see it in one side, left side of the resistor, I mean diode, you can see one black band, no? That particular band, that particular side in which the band is available is cathode, and the opposite direction, opposite terminal is the anode port. Zener diodes are designed to operate in reverse breakdown. We know that already. Two types of reverse breakdown in a Zener diode are avalanche breakdown and Zener breakdown. The avalanche breakdown occurs in both the PN junction diode or rectifier diode and Zener diodes at a sufficiently high reverse voltages. Zener breakdown occurs in a Zener diode only at low reverse voltages. This is a very important difference between avalanche breakdown and Zener breakdown. Avalanche breakdown will occur in both the diodes when at what value means at high reverse voltages. But Zener diode at low reverse voltages it will occur, and it will only appear in case of Zener diodes, not in case of PN junction diodes. A Zener diode is a heavily doped diode to reduce the breakdown voltage. This causes a very thin depletion region. The Zener diode's breakdown characteristics are determined by the doping process only. The commercially available voltage breakdowns of Zeners will be 1.8 volt to 200 volt. 1.8 volt to 200. A Zener diode is much like a normal diode. The exception being is that it is placed in the circuit in reverse bias and operates in reverse breakdown ratio. You can look at the circuit or the VI characteristics which is shown here. These two diagrams only, it makes the difference. See, the diagram which is shown as subdivision B is the actual the characteristics of a Zener diode. So what happens is there is a small gap from the origin to that particular reverse breakdown region, or VZ is reached, no? Okay, there is a small gap from origin. But if you look at for a PN junction diode, what happened is that particular gap, it won't come. That is, till that point breakdown is reached, for a PN junction diode, till that particular point there is no current at all. But what happens in Zener diode is, till breakdown is reached, even though breakdown is not reached, small amount of current will be there. But once breakdown reaches, either avalanche breakdown or Zener breakdown, once it gets reached up, then current will rise rapidly or sharply. Okay, that is what is the difference I want to state for Zener and avalanche breakdowns. Breakdown characteristics, look at this very clearly. As the reverse voltage VR is increased, the reverse current IR remains extremely small up to the knee of the curve. That particular voltage, the other name is knee voltage also. Okay, knee voltage. The reverse current is also called the Zener current, IZ. At this point, what happens is breakdown effect will begin. The internal Zener resistance, also known as Zener impedance, ZZ, begins to decrease as reverse current increases rapidly. So according to Ohm's law, once the current is going to rise, automatically resistance or impedance will get decreased, because both these two, current and impedance or resistance, are inversely proportional to one another. Okay, that is what is the breakdown characteristics of a Zener diode is concerned. Then comes a small comparison between Zener diode and avalanche breakdown. Zener breakdown and avalanche breakdown. So very simple. This Zener breakdown occurs at junctions which, being heavily doped, have narrower or depletion layer to be very much small, narrowed down. Avalanche breakdown, that's what I said, the thickness of the depletion layer gets reduced for Zener breakdowns. But avalanche breakdown, what happened is, this breakdown occurs at junctions which, being lightly doped and have wide depletion layer. Number two, Zener breakdown voltage sets a very strong electric field across the narrow layer of the depletion. But here in avalanche, electric field is not that much strong enough to produce Zener breakdown. Here, that's in Zener breakdown, electric field is very strong to rupture the covalent bonds, thereby generating electron hole pairs. So even a small increase in reverse voltage is capable of producing large number of current carriers. But here, avalanche breakdown, minority carriers, they collide with semiconductor atoms in the depletion layer, which breaks the covalent bonds which is already formed, and electron hole pairs are thus generated. Newly generated charge carriers are accelerated again by the electric field, which results in more collisions and thus generates avalanche of charge carriers. This results in avalanche breakdown. Finally, the very important difference is Zener diode exhibits negative temperature coefficient. That is, breakdown voltage decreases as temperature increases. But as far as the avalanche breakdown is concerned, avalanche diodes, or I can say rectifier diodes, or PN junction diodes exhibits positive temperature coefficient. That is, breakdown voltage increases with increase in temperature. So these are all the differences I want to tell regarding these two breakdowns are concerned, right? Next comes yeah, this is what this diagram is showing you, the PN junction breakdown characteristics, but it will combine both our avalanche breakdown and Zener breakdown. Both will be combined together here. Then comes the applications of Zener diode. So Zener regulation, Zener diodes, it finds applications for voltage regulations. It is a very important application wherein I can use the Zener diodes. Okay, so Zener regulation with a varying input voltage is the first application, which is very, very important and foremost. Then Zener limiting, then waveform clipping. Waveform clipping means you might have studied clipper and clamper circuits, right? So whichever part for an input sine wave, if I don't want, or if I want to clip the negative half input, then I can make Zener diodes to be used there. I can clip the unwanted portions of the waveform neatly by using a Zener diode. Ordinary diode can also be used, but Zener diodes are also it can be employed. Then clamper circuit also it finds application. Clamper circuit, the other name is voltage shifter. If I want to shift the DC level or the waveform to the upper portion or to the bottom portion of the waveform or the cycle, that can be done very neatly with the Zener diode. Then surge protectors, that also can be done. And RNG means random number generator. As far as the mathematics is concerned, this particular thing is a very important thing, random number generator. That can also be done by making use of Zener diodes. So to summarize, finally, a Zener diode is always operated in its reverse biased condition. That is a well-known fact. A voltage regulator circuit can be designed using a Zener diode to maintain a constant DC output voltage across the load in spite of the variations in the input voltage or changes in the load current. A voltage regulator, as I said, that is the important application as far as Zener diodes are concerned. The Zener voltage regulator consists of a current limiting resistor RS connected in series with the input voltage Vs, with the Zener diode connected in parallel with the load RL in this reverse biased condition. Then the stabilized output voltage is always selected to be the same as the breakdown voltage of the diode VZ. So as these diodes you might have studied a lot, just I ran through the points which I want to discuss with you. Okay, so that's it about the Zener diode and PN junction diode. So next comes some of the videos. So as usual, I'll give you some video links that you can go through actually, and with that is the end of the slides actually. I'll stop sharing the screen here. I'll come to the link now, and here I'll be giving you the YouTube video link in the chat box that you can see it. 1 minute. I'll share the video link. Diodes, yeah. A lot of animations are there. Okay, I'll open up this. See, for diodes and Zener diodes, nearly totally 3 YouTube videos I have got. Right. I'll put all the 3 in the chat box. You can make use of it. First 2 are for ordinary diodes, and third is for Zener diodes. So you can look at the this thing. What is it? Chat box. You can take the links for YouTube videos. Okay, that can be done. Similarly, um, I'm having a animation video also here, a simple explanation and animation of. Uh, okay, so this animation video alone, I will run to you. You can enjoy. 1 minute, I'll share that particular thing. 1 minute. Uh, sorry, this is not. 1 minute, students. I am opening it. One minute, I'll share it. Yeah, I think now you can see. So there is a small video I wanted to present to you. Okay, with that we will stop our session. Time is 2:59. 1 more minute. So thank you so much for patient listening.